Thermodynamics in Biosystem Module 4 Properties of Pure Substance Segment 4 Property Tables. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about phases of a pure substance, phase change processes, and property diagrams. In this segment, we will discuss about property tables. For most substances, the relationships among thermodynamic properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Some thermodynamic properties can be measured easily, but others cannot and later are calculated by using the relations between them and measurable properties. The results of these measurements and calculations are presented in tables in a convenient format, for example, steam tables. For each substance, the thermodynamic properties are listed in more than one table. In fact, a separate table is prepared for each region of interest, such as the superheated vapor, compressed liquid, and saturated mixture regions. Property tables are available in appendix of the textbook. In the analysis of certain type of processes, particularly in power generation and refrigeration, we often encounter the combination of properties U plus PV. For the sake of simplicity and convenience, this combination is defined as a new property, enthalpy, as shown in equation 4.1 and 4.2. In some tables encountered in practice, the internal energy U is frequently not listed, but it can always be determined from U equals to H minus PV. Saturated liquid and saturated vapor states. The properties of saturated liquid and saturated vapor for water are listed in tables A4 and A5. The subscript F is used to denote properties of a saturated liquid, and the subscript G to denote the properties of a saturated vapor. Another subscript commonly used is Fg, which denotes the difference between the saturated vapor and saturated liquid values of the same property. The quantity Hfg is called the enthalpy of vaporization or latent heat of vaporization. It represents the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. It decreases as the temperature or pressure increases and becomes zero at the critical point. Saturated liquid vapor mixture. During a vaporization process, a substance exists as part of liquid and part of vapor. That is, it is a mixture of saturated liquid and saturated vapor as shown in the left figure. To analyze this mixture properly, we need to know the proportions of the liquid and vapor phases in the mixture. This is done by defining a new property called the quality X as the ratio of the mass of vapor to the total mass of the mixtures, as shown in equation 4.3. The quality of a system that consists of saturated liquid and the quality of a system consisting of saturated vapor is 1. In saturated mixtures, quality can serve as one of the two independent intensive properties needed to describe a state. During vaporization process, only the amount of saturated liquid changes, not its properties. The same can be said about a saturated vapor. A saturated mixture can be treated as a combination of two subsystems, the saturated liquid and the saturated vapor. However, the amount of mass for each phase is usually not known. Therefore, it is often more convenient to imagine that the two phases are mixed well, forming a homogeneous mixture. Then the properties of this mixture will simply be the average properties of the saturated liquid vapor mixture under consideration as shown in equation 4.4. Superheated vapor. Since the superheated region is a single phase region, which consists only vapor, temperature and pressure are no longer dependent properties, and they can conveniently be used as the two independent properties in the tables. The format of the superheated vapor tables is illustrated in the left figure. In these tables, the properties are listed against the temperature for selected pressure starting with the saturated vapor data. The saturation temperature is given in parentheses following the pressure value. Compared to saturated vapor, superheated vapor has a lower pressure, higher temperatures, higher specific volumes, higher internal energies, and higher enthalpies than the superheated vapor. Compressed liquid tables are not as commonly available. One reason for the lack of compressed liquid data is the relative independence of compressed liquid properties from pressure. Variation of pressures of compressed liquids with pressure is very mild. Increasing the pressure 100 times often causes properties to change less than 1%. In the absence of compressed liquid data, one can treat compressed liquid as saturated liquid at the given temperature. This is because the compressed liquid properties depend on temperature much more strongly than they do on pressure, which can be expressed by equation 4.5. In general, a compressed liquid is characterized by higher pressures, lower temperatures, lower specific volumes, lower internal energies, and lower enthalpies. Reference states and reference values. The value of U, H, and S cannot be measured directly, and they are calculated from measurable properties using the relation between thermodynamic properties. However, those relations give the changes in properties, not the values of properties at specified states. Therefore, we need to choose a convenient reference state and assign a value of 0 for a convenient property or properties at that state. In thermodynamics, we are concerned with the changes in properties, and the reference state chosen is of no consequence in calculations, as long as we use values from a single consistent set of table or charts. In the next segment, we will discuss about ideal gas equations of state. Until then, I am Yusuf from Institut Teknologi Bandung.